Welcome back. In this video, we are going to solve example 1.3 that is taken from chapter number 1 stress and book name is Mechanics of Material by RC Hibbeler 9th edition. So statement of the problem is determine the resultant internal loading acting on cross section at G of the beam shown in figure 1.6a. Each joint is pin connected. So you can see this is the structure and this is the beam. Clear? This is the pin joint. So you have to determine the resultant internal loading at point G. And there is a point load at point A which is 1500 pound. So we will find NG normal force at point G, shear force at point G and moment at point G. So let's start with the solution. So you can see that for taking the internal load at joint C, we will need this section. So where I have this force and this force, so we will need this force AB. So how we'll find this? So for that, I have to remove this reaction pin support at point C. So when you remove it, so this pin support, pin support is offering reaction force FBC in this direction. Clear? And when you remove this pin support at point A, so it will offer a horizontal reaction force which is equal to EX as well as vertical reaction force EY. Okay, why we are taking FBC only as horizontal force? So note that BC is a two force member since only two force act on it. So for this reason, the force at C must be along BC. So which is shown as horizontally. Now we'll find this FBC, EX and EY by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along x direction must be equal to 0 and force toward right is taken as positive. So FBC minus EX will be equal to 0. So from here we will get this FBC is equal to EX. But its value is not known. So we will write this as equation number 1. Now this EY can be obtained by using another equation of equilibrium that sum of all forces along y direction must be equal to 0 and force is taken as positive. So one force which is 1500 that is downward. So minus 1500 plus this EY is upward. Clear? And you can see there is a triangular load that is shown over here. So we will convert this into a point load. So how you will convert it? So for that, if I convert it into point load, so it will be equal to 1 over 2, its magnitude which is 300 and the length over which it acts is 6. And that will give you 900 pounds. Okay, but it will act at a distance of 2L by 3 from point E. So 2L, 2 into 6 is 12 divided by 3 is give you 4 feet. So 4 feet from point E and 2 feet from point D. 2 feet. Okay. So this force is minus 900 pound is equal to 0. So from here you will get, when you calculate, you will get EY will be equal to 2400 pounds. Okay. Now we have EY. So what we will do is that we will apply third equation of equilibrium, and the third equation of equilibrium is that sum of all moments about point E is equal to 0 and taking the counterclockwise moment as positive. So about point E, the first moment will be due to this 1500 pound loads and perpendicular distance is this, if you add them, this is 10 feet and this is producing counterclockwise, so it will be positive. So I will write 1500 multiplied by 10. Now the second moment is produced due to this 900 pound load and that is acting at a distance of 4 feet and it is also producing counterclockwise, so it will be positive. So I will write plus 900 multiplied by 4. And the last force that is producing moment about point E is this FBC and perpendicular distance is 3 and this is producing clockwise, so it will be negative. So minus FBC multiplied by 3 is equal to 0. So when you solve this for FBC, you will get FBC will be equal to 6,200 pound force. Okay, now this you have FBC, so we need this FAB. So what we will do is that we will use method of joint at B. So for that we will take this B point, clear, and at B point you can see you have this FBC in this direction. So I will write this FBC in this direction, which is equal to 6,200 pound, and at point BD we have this member, so it will exert a vertical force which is FBD. Okay, this will be FBD, and this FBD is not known yet. And this member FAB will also act a force in this direction on joint B. Okay, FAB, and you can see that this side is 3 feet and this side is 4 feet. This is 3 feet, this is 4 feet. By Pythagoras theorem, this FAB will be 5. So what if I draw a ratio for the triangle 3, 4, 5? So it will be, let me draw it. This is 3, this is 4, and this is 5. So this is the joint B having force FBC, FBD, and FAB. So we'll find these forces by using equation of equilibrium. So first equation of equilibrium is that sum of all forces along x direction must be equal to 0 and force toward right side is taken as positive. So on right side we have one force 6,200, clear. Now this force FAB will be having two components, one along x direction and one along y direction. So this component will be equal to FAB into 4 divided by 5. How? Because you can see that this is theta. So we will take cos theta is equal to this FAB x component divided by FAB. So FAB is FBX. FAB x component will be equal to FAB cos theta. So FAB is there and cos of theta is equal to 4 divided by 5. So this component FBX, you can see this is equal to 4 over 5 multiplied by FAB. And this is in negative direction, so I can write FAB into 4 divided by 5 is equal to 0. Okay, when you solve this, you will get this FAB will be equal to 7750 pounds. Okay. Okay, now we know that this is the first equation of equilibrium. So second equation of equilibrium is that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So upward force is FBD, clear, and the another force that is downward is this component, which is FABY component, and this FABY component will be equal to FAB into 3 by 5 because sine theta is equal to 3 over 5. So I will write minus this FBD minus FAB. FAB is 7750 and this 3 over 5, that is equal to 0. Okay. Now when you calculate this FBD, so FBD will be equal to 4650 pound. Okay. Now you have these forces. So what we will do is that we will cut this beam at point G and draw the free body diagram. It will be like this, clear. So one force is 1500 and another force will be FAB. So in order to find the reaction forces, so if I take the section at G, so here at this point A we have 1500 pounds load, clear, and this is FAB, which is in this direction, and this is FAB, that is equal to 7750 pounds, and the ratio of their triangular side is the same. This is 3, this is 4, and this is 5. So this is point G. So when you cut it, so you'll be having a normal force in horizontal direction, which is NG. You will be having a shear force that will be acting in this direction, which is VG, and you will be having a moment at point G, which is equal to mg. Oh, and the length of this AG is 2 feet. 2 feet. Let me show you over here. You can see this length is 2 feet. Okay. So what we will do is that we will apply equation of equilibrium in order to find this mg, ng, and vg, which are the internal loadings. So for that, I will apply equation of equilibrium, that sum of all forces along x direction is taken as positive, x is equal to 0, and force toward right side is taken as positive. So one force, which is ng, is taken as in positive direction. Clear? So I will write this ng, and the second force is this horizontal force of FAB, which is again equal to FAB into cos of theta. This is theta. So cos of theta is 4 divided by 5. So FAB multiplied by 4 by 5. So plus FAB, which is 7750 into 4 divided by 5, is equal to 0. So from here, this NG will be equal to minus 6,200 pounds. Negative sign mean that your assumed direction NG toward right side is wrong. It should be in toward left hand side. Now we will apply another equation of equilibrium, that sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So 1500, which is acting downwards, so minus 1500 plus this vertical component of this force. This is the vertical component, and this will be equal to FAB into sine of theta. So sine theta is 3 by 5. So I can write this FAB multiply by 3 over 5. FAB is again 7750 multiply by 3 over 5 minus this VG, which is downward acting, is equal to 0. So from here you will get shear force at point G comes out to be 3150 pounds. Now the last thing is the moment about point G. For that we will apply equation of equilibrium, that sum of all moment about point G is taken as 0, and counterclockwise moment is taken as positive. So first moment is this 1500 into perpendicular distance is 2, and it is producing counterclockwise movement, so it will be positive. So I can write 1500 multiply by 2. The second moment is due to this vertical force, which is upward, and perpendicular distance is 2 feet. And this is also producing clockwise movement, so it will be negative. So vertical component, you can see this was the vertical component, 7750 into 3 by 5, and perpendicular distance is 2, as it is producing clockwise movement, so it will be negative. And the last movement, which is counterclockwise at point G, react, which is internal movement, that is equal to 0. So when you solve this, you will get moment at point G comes out to be 6,300 pounds into feet. And these are the NG, VG, and MG are the internal loading for the beam at portion AG. And that was all about this example problem 1.3. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching.